Good thing. So if we have an inner automorphism, let's take an example in a second. It's a inner automorphism is basically a group automorphism from a group to itself when it's created by conjugation by an element of the group onto the rest of the elements in that group. And so a good example would be, for example, S3. But let's first denote some notation. So we can denote it as some automorphism of by element G, which basically means it goes from a group G to G, and this applied to some element A for every element in G basically will mean G times A times G inverse. So you conjugate every element, other element in the G by including itself by itself perhaps by some chosen element, some chosen for G inside the group. You pick a G inside the group and multiply it normally on the left side to every element, and at the same time its inverse on the right side of it. So for example, for S3 that consists of these cycles, we have 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, and 2, 3. We would do a similar thing, and we can find the mapping. And it's, of course, automorphism is an isomorphism, going to have the same cardinality like the original group, and it will be a bijective homomorphism and endomorphism at the same time. That's the definition of an automorphism, all right? So an endomorphism to the group to itself, that's also isomorphic. And so let's see, for example, in the case of S3, what will happen? Well, if we choose, for example, G to be 1, 3, all right, so actually it's denoted more like this, we could. So this conjugation by 1, 3, and we will do it for every element. So on 1, 2, 3, what will it produce? Well, it would mean 1, 3, 1, 2, 3, and 1, 3 inverse, but 1, 3 and 1, 3 inverse is the same thing, so we don't have to write the inverse, but anyway, I mean, let's just keep the practice from the definition here, and that would generate 2, 1, 3. 2, 1, 3. And then we can do that for the rest of the elements as well. Obviously, what will happen for 1, 3 itself, 1, 3, 1, 3, and 1, 3 again, I can say inverse, but that generates actually the identity element. So this is the identity element of the graph, we note that E. Then we're conjugating still 1, 1, 3, always conjugating by 1, 3. 1, 2 will do what? 1, 2 will again conjugate by 1, 3, so the result of this will be 2, 3. Then for 2, 3, 2, 3, so that is 1, 3, 2, 3, 1, 3 inverse. That's going to be 1, 2, and 1, 2, 3, 4, 5, and we need a sixth one, and that will be again by 1, 3 onto 1, 3, 2, 1, 3, 2. This one basically. Well, just like this one led to this one will lead to this one will lead to this one. So we will have basically 1, 2, 3. All right, and I mean the way you write them in an order, the loop goes like this. I mean that's just notation of cycles. So this is 1, 2, 3 is the same like 2, 1, 3 is the same like 3, 2, 1. It doesn't matter where you start. You always go to the last one, then you begin from the left again. All right. So anyway, here we list it out. We see that 1, 2, 3 is mapped to this one is mapped to this one, and you just do it by the cycle multiplication. All right. So we got that, so this is a mapping for S3 example. Also, let's see how it works with inverses for in an automorphism of a group. So that in automorphism in general, we can also invert it, and if it acts with itself, basically with its inverse, it should give the identity And how does that work? Well, for any element inside the G, we can take the we can say that basically this would be we can write it like this. So what we would get by this is we conjugate in a reverse order right here because this is inverted, and then that's in the inside of the function. On the outside we conjugate it normally by G, as we see. Well, these things will become identity. So it's identity times A times identity, so it's A. So that function will map it, will be the identity mapping. Alright, so the identity mapping, basically the identity mapping is a result when you put it in operation with its own inverse. That's expected, of course. And let's also see how it becomes a homomorphism. So for any AB in G, let's see how it acts on both of those elements. Well, if we apply it to AB, what happens is we get G, AB, G inverse, and we can put an identity in the middle. That's the trick we'll use for this sort of homomorphism, to show that it's a homomorphism, that we do get eventually this. Alright, we want to know, this is definition of a homomorphism. We want to know that under the function, the product of AB is the same as the function of A in product with the function of B. Well, I can put an E equaling to G inverse right here. So I would get G A G like this. G inverse G. So G A G inverse. G again. So I just put this in the middle of this string. We have the associativity, so it should work out because of that. So we get GB G inverse and GA G inverse, which is nothing different than the automorphism, the conjugation applied to A times the conjugation applied to B. So here we have also showcasing the basic homomorphism formula there also. Alright, so this was a short intro to automorphisms and inner automorphisms of a group. So once again, to repeat, they are the automorphisms that arise when you conjugate, and the conjugation function is basically you take an element from the group, and any element A in that group will be conjugated in the following manner. Apply the element on the left side, and also at the same time apply the inverse of the element on the right side, the result of the conjugation. And one more thing, of course, in automorphism of a commutative group will be very trivial, because conjugation doesn't have a big effect with commutative groups, because commutativity would move this. If the group is commutative, we would have G inverse reducing to identity and A would be left. So the conjugation doesn't cause some changes in commutative cases. Alright, so that's conjugation right here. And in automorphism is we pick some element to conjugate all the other elements by, and then the result of that, so where it maps. And that's the same thing as automorphism in general, because there's more automorphism. Inner automorphism is the special case when it arises by conjugation, but there's automorphisms more generally, and inner automorphisms are a subset of automorphisms of a group.